So, Professor, thank you for your kind introduction. I am Atsushi Ohtaka, and my specialty is organometallic chemistry and catalytic chemistry. So, uh, it's a little bit difficult, different from sort of viewers. And my research topics is the catalytic reaction in water with metal nanoparticle as a catalyst. So now I would like to talk to you about application of polytetrafluorescence as a support for metal nanoparticles. In the past several decades, chemical transformation in aqueous media have attracted tremendous attention from both academic researchers and industrial scientists. And because of advantages such as reaction rate acceleration and worker procedure simplification. In addition, water is safe, abundant, non-toxic, and inexpensive. The exploration of catalytic reaction with metal nanoparticle-based heterogeneous catalyst in new water is increasing dramatically because they can prepare easily and stable even in water. And they exhibit unique surface properties, high specific surface areas, and high catalytic activity in water. However, they have some drawbacks. One major drawback is that the metal nanoparticles tend to lose their catalytic activity during use. This is consequence of formation of aggregates owing to their high surface energy via so-called Ostwald ripening. For this reason, a number of different solid support materials for metal nanoparticles have been investigated, including metal organic frameworks, covalent organic frameworks, magnetic supports, natural polymers, synthetic polymers, and mesoporous supports, and so on. In our laboratory, to prepare the recyclable metal nanoparticles, we took notice of two reports. One is about dispersion polymerization. In this polymerization method, a polymer are deposited because they are insoluble in reaction medium and then make particles with uniform size. The other is Professor Kobayashi's report. They prepared a polymer encapsulated palladium catalyst, and in this paper, they described the catalyst would be immobilized by the interaction between pi electrons of benzene rings or polystyrene used as a polymer backbone and vacant orbitals of the metal. Based on the idea that metal nanoparticles with a fairly uniform size will be stabilized on polymer supports by hydrophobic interactions in water, our group successfully developed linear polystyrene stabilized palladium and platinum and rhodium nanoparticles. And they have high catalytic activity for these reactions and usability, as shown here. Although we developed the effective reusable nanoparticle catalyst, as shown here, we thought they are difficult for industrial application because they are the powder. So on the other hand, Teflon coated glass equipment and several equipment made of Teflon are often used in laboratory. Considering industrial applications, it's important to develop uh, Teflon-supported metal nanoparticles, which have high catalytic activity and reusability. And some examples in which PTFE is used as a support for metal nanoparticles are reported. Based on this background, we decided to investigate our methodology for preparation of metal nanoparticles using PTFE as a polymer supports. So to prepare PTFE stabilized palladium nanoparticles, the mixture of PTFE, palladium acetate, for methyl phenylboric acid, and the gas potassium hydroxide solution was stirred at 90 degrees Celsius for 5 hours to give the black powder. And when the black powder obtained was observed by TEM, a fairly uniform particle was confirmed. The size is 2.4 nanometer. And in contrast, although the particle size was similar around here, most of palladium are formed aggregates, as shown here, when the nanoparticles were prepared in the absence of PTFE, suggesting PTFE acted as the stabilizer for palladium nanoparticles. And an XRD pattern for the black powder is presented here. In addition to the diffraction peak of PTFE, the other diffraction peak ascribed to palladium were observed. And another broad peak was observed in addition to peak of ascribed to PTFE in XPS spectrum. A fluorine has more partial positive charge due to coordination to palladium nanoparticles, thereby justifying the shifting of peak position to higher energy range in PTFE palladium nanoparticles. That is, it's considered that palladium nanoparticle will be immobilized on PTFE through the interaction with fluorine. And PTFE stabilized rhodium nanoparticles were also prepared using a sodium borohydroxide as a reductant in the presence of TBAB. The formation of PTFE rhodium nanoparticle was confirmed by TEM and XRD spectra. The model. So from these results, it will confirm that PTFE can be used as a support for palladium and rhodium nanoparticles, and then the catalytic activity is nanoparticle was examined. Hi, Professor, is it turn off the mobile phone? Okay. Now the mic. So first, we have the turn off the mic. So first, we evaluated the catalytic activity of PTFE-supported palladium nanoparticles using the Suzuki coupling reaction as a model reaction. When the reaction was performed using several bromide with various substituents, both the electron-rich and electron-deficient bromide with reactive, affording the desired coupling products in high to moderate yield. The low yield, in the case of the 4-brom-nitrobenzene, would be caused by the reaction of 4-brom-nitrobenzene with the catalyst would be solid-solid reaction because of the high melting points of 4-brom-nitrobenzene. Indeed, the coupling product was obtained in 95% yield when performing the reaction in the presence of TBAB. And when the coupling reaction was performed using several arabonic acid, the yield of coupling product decreased with decreasing electron density on the aromatic ring. When the recycling experiment was performed under these reaction conditions, the catalyst was recycled at least 9 times without any loss of activity. And no palladium species were observed in the reaction medium after the reaction as confirmed by ICP-AES analysis. Similarly, similarly size of palladium nanoparticle and no aggregate were observed by TEM after the recycling experiments. It's very important point. This catalyst is very useful for this reaction. And we next investigated the catalytic activity of PTFE-supported palladium nanoparticles for Heck reaction in water. A variety of allyl iodide was successfully coupled with styrene to afford the desired product in good yield. Although the coupling product was obtained in excellent yield from the reaction with 4-chlorostyrene, a moderate yield was observed in the case of 4-methoxystyrene. And when the recyclability of the catalyst was examined under these reaction conditions, a slight catalytic deactivation was observed from 91% to 71%. From TEM image of the recovered catalyst, several aggregates shown here are larger than 5 nanometer, and polymer portion in which palladium nanoparticles are not present were observed around here. These data suggest that the ostward ripening occurred during the reaction. And when the mixture of silbenzene and PTFE stabilized rhodium nanoparticle was stored at room temperature in water and the hydrogen pressure for 15 hours, and 97% yield of cyclohexyloctane was obtained. The catalyst was recycled at least 4 times without any loss of activity, and no detectable rhodium species were observed by ICP-AES analysis in the reaction solution after the reaction. However, and the larger particle size and the broader size distribution were found by TEM analysis and observation of the recovered catalyst. So in this case, the Oswald ripening also occurred during the reaction. In summary, we confirmed that PTFE can be used as a support for palladium and rhodium metal nanoparticles, and these nanoparticles show high catalytic activity and reusability for Suzuki coupling reaction, Heck reaction, and alane hydrogenation. So this work was performed by these members. We wish to thank Professor Wozumi and Dr. Hamasaka for our Institute for Molecular Science for assistance with TEM measurements. And we also thank Dr. Shinagawa of Osaka Research Institute of Industrial Science and Technology for assistance of ICP-AES, XPS, and XRD measurements. And thank you very much for your kind attention.